All right, well, we'll go ahead and get started here. Welcome to our fourth quarter webinar on themes of the new economy, beyond Moore's Law, an overview of semiconductors. My name is Sean Morgan. I'm the manager of investment marketing. I'm joined by our educator on the subject, Christian Say, who is one of our associate research analysts here. Christian, go ahead and go to our disclosure slide. Before we begin, I do want to note that this presentation expresses the views of Eventide, and there is no guarantee that these views are accurate. In fact, they may be proven to be wrong. So this presentation is meant to be informational only and not used for investment advice. Now, as a way to provide framework for understanding this webinar, let me explain in very brief Eventide's approach. We are a fundamental asset manager, meaning we deeply consider the fundamentals of each individual company as a primary way to assess its value in our portfolios. Now, a part of considering a company's fundamentals is considering both what a company does and how it does it. So we use a proprietary framework called Business 360 that helps us examine how a company operates through the lens of how it treats each of its key stakeholders, its customers, its employees, its suppliers, host communities, the environment, and society more broadly. Then, when we're looking at what a company does, we do so by identifying these broad secular trends in the economy and determining which of these trends a company is positioned within. We call these trends themes since they tend to transcend short-term business cycles and they persevere based on their propensity to transform the economy. So the themes that we identify as being important for solving important human problems, we call those themes of human flourishing. So these are themes like big data and the Internet of Things, or clean water technology and supply chain resiliency. Now, one of these themes is what we call beyond Moore's Law, to which many of our investors say, what is that? So hopefully this webinar sheds light on what this theme is by talking about one of its main business drivers, which is semiconductors. Semiconductors are complex and many people don't understand them, including myself, which is why we have an expert, Christian Say, here to help explain it. So we will have time for Q&A at the end. So submit your questions along the way in the Q&A tab at the bottom of your screen. As you notice, Christian and I are both in our Eventide fall uniforms. We have our
I was just gonna say that. I was gonna say another disclosure is that Eventide does not require that we wear the exact same outfits, but great minds just think alike.
But we didn't plan that. It's just our uniform in the fall. Like throw on the vest instead of ironing your shirt, you can throw on a vest and it covers up all the wrinkles. Well, so with that, Christian, welcome. Tell us about some semiconductors and beyond Moore's Law.
Great, thank you so much, Sean. So thank you everyone for joining us. So I'd like to just get started by bringing up what's on top of mind for, I'm sure, most people on this call, the semiconductor shortage, right? So why is there a chip shortage? We've all seen it in the news. There's this massive chip shortage and it's been going on all year. So, because of this shortage, actually, this is a photo I think is pretty incredible. So these are Ford F-150s that have been built at a factory in Detroit, rolled off the production line and straight onto a parking lot because they can't be sold, because they're waiting for just a handful of semiconductor parts. These are $30,000, $40,000 vehicles that are unable to be sold because of a handful of what are mostly single dollar parts. And I think this really gets to, just what a big impact and an unexpected impact this shortage has had on pretty important players in our economy. So how did we get here? Why is there a shortage? Without pretending that there's a simple answer, because there really never is, I will say that there's one important factor that I think isn't always fully understood, and it's very important. So basically, old economy manufacturers, automakers in particular, have consistently underestimated the importance and complexity of semiconductors. How do I know that? Well, just look at the difference between companies like Toyota and Tesla versus companies like Ford and GM. So for every 100 vehicles Ford and GM, or each of these companies, made at the start of 2020, so at the start right before the pandemic, for every 100 vehicles that they made then, Ford and GM last quarter, Ford made 78, so down 22%, and GM made 72, so GM was down 28%. Now compare that to Tesla. For every 100 vehicles Tesla made at the start of 2020, last quarter, Tesla made a record-breaking 273. So Tesla was up 173%. Toyota made 114, so up 14%. And that looks slightly less impressive until you realize that last quarter was only the second time in history Toyota outsold GM to become the #1 automaker in the United States. And the first time that happened was actually last quarter. So the last quarter and this quarter, it's been a pretty impressive streak for Toyota. Clearly, the chip shortage has affected different companies differently. What caused that? What's the difference? What's the difference between a Toyota and a Tesla and a Ford and GM? Well, let's see what Tesla said last quarter. Expertise in the chip industry made a huge difference. We never reduced our production forecast with our suppliers. Expertise in the chip industry made the difference. So Tesla has the most sophisticated in-house semiconductor capabilities of any auto manufacturer in the world. In fact, Tesla actually makes its own chips. And if you actually saw the news today, you can see at least Ford is learning this lesson here, where Ford just today in the Wall Street Journal announced that they're going to start looking to make their own chips as well. So that's Tesla. Clearly, Tesla has understood the importance and complexity of semiconductors. Well, what about Toyota? Toyota traditionally, Toyota actually went through this before. So in 2011, after the Toyota experienced a pretty severe semiconductor shortage. And at that point, Toyota realized, hey, wait a second, these are very small parts. They're relatively inexpensive, a few dollar parts, $30,000 vehicle, relatively inexpensive, but they can take down our production line for months. It's not that hard to store them. So what did they do? Starting 10 years ago, Toyota asked its suppliers to stockpile semiconductors for them, up to 6 months worth of semiconductors. And clearly that's helped Toyota weather this storm relatively well. So, the results really show what a difference an understanding of semiconductors make. And it really speaks to, I think, one of the primary factors behind the shortage, which was really that the old economy manufacturers, they underestimated the importance and complexity of semiconductors. Now, as investors, we don't want to make that same mistake. So hopefully that's why you're here today. And my goal with this presentation is for you to leave with a basic understanding of what a semiconductor is, how semiconductors are made, and finally, what the heck is beyond Moore's law, right? So there's a lot in the news about semiconductors, and I want to provide you some context so that you can understand that news and then go on to make better, more informed decisions. So what is a semiconductor? All right, at the risk of stating the obvious, a semiconductor is a semiconductor. So that means it's a kind of material that sometimes acts like a conductor and sometimes acts like an insulator. So it's a material that sometimes will conduct electricity like a copper wire, and sometimes it will block electricity like a block of wood. What's important about that property of this material is that we can control when the semiconductor acts like a conductor and when it acts like an insulator. Think of it like having a dial where we can dial the material up to be more like a copper wire or more like a block of wood. So why does it matter that we can do that? Well, by dialing up the material to be more like a copper wire or more like a block of wood, to be more like a conductor or more like an insulator, we're able to build devices that can control electricity. And the way we control electricity using semiconductors, we typically do that in one of two ways. And I think the two light switches that I've put on here are good analogs for how we do that. So the first way, and the way we typically think of, is that we're able to turn off and on the electricity. So just like a light switch where it goes off, on, with the semiconductor, by very quickly going from conductor to insulator, copper wire to block of wood, we're able to basically flip on and off the electricity. And think of that as digital. So we often hear digital versus analog. That's pretty close to how we think about with digital. So with digital, on, off, that's 1, 0, 1, 0. Very quickly, you're able to build out binary, and with binary, able to build out logical functions, and from there, you're able to build out computational devices. Now, on the other hand, another way to control electricity is think of it like a dimmer switch, where by dialing the semiconductor material to be a little more conductive or a little less conductive, we can allow more or less electricity to pass through. And that typically corresponds to analog use cases. So we use semiconductors for things like amplifying radio signals, or if you think of actually, like a guitar amplifier, that kind of amplification, what you're doing is you're taking the electrical signal from the guitar and you're dialing it up like a dimmer switch. So that's another use case for how we can use semiconductors. So two primary ways that we control electricity with semiconductor devices, like a digital switch, off, on, or a dimmer, kind of a sliding switch. Okay, so we have semiconductor materials. From those, we make light switches, basically. Why do we care? Why do light switches matter? Well, as it turns out, switches are super important. Switches are one of the fundamental building blocks of all modern electronics and are arguably the most important building block of all modern electronics. If you took apart your laptop or took apart your phone, zoomed in really, really close to the processor, like zoomed in very, very close, what you'd end up seeing is basically just billions of tiny switches crammed together. Switches are the fundamental building block of modern electronics. Now, before semiconductors, we still needed to control electricity for any sort of electronics. So we still needed switches, but we didn't have semiconductors. So what did we use? We used vacuum tubes. That's what you see there on the left. So vacuum tubes are big, slow, expensive, and unreliable. They would burn out. And so with the invention of the transistor, so the transistor is what we call a switch made out of a semiconductor. That's a pretty important term, transistor. You'll hear that whenever we're talking about semiconductors, and you'll hear that term throughout this presentation. So with the invention of the transistor in the 40s, we were able to create electric switches that are orders of magnitude better. So that's what you see there on the right. That's a single semiconductor switch. So that's a single switch made out of a semiconductor device, and that's a single transistor. And actually, that photo comes from it actually comes from from Amazon. It's there was a listing for something like 200 of these little devices for something like $5, right? So it gives you a sense of how cheap these are. These are just, they call them, bubble gum or jelly bean parts. Now, what you're seeing there looks a lot smaller, it looks a lot more efficient, but actually what you're seeing there isn't actually the semiconductor. The actual semiconductor is inside of that black cylinder at the top. And so if I cut that black cylinder at the top in half, what you might see is something like this, okay? So that tiny square in the middle, that's the actual semiconductor switch, okay? So inside that black cylinder, that's the semiconductor switch. But it's so small that we need to be able to plug it into a board, we need to actually put it in a package, attach some little tiny wires to the semiconductor switch, then attach those tiny wires to some bigger wires. That's what you see at the bottom, those three prongs. And that allows us to then plug that switch into a board, okay? So that's what a semiconductor switch, a transistor, looks like. Now, when I said that semiconductor switches, transistors, were a lot smaller and more efficient, that's a bit of an understatement because they're a lot smaller and a lot more efficient. In 1995, researchers from the University of Pennsylvania, they recreated the ENIAC, which was a supercomputer built during World War II. They recreated the entire ENIAC on a chip that was smaller than a dime. So that's what you see on the right. That's the ENIAC chip, and it was built for the 50th anniversary of the ENIAC. So the ENIAC, what you see on the left, was the fastest supercomputer in the world, built during World War II, and it used vacuum tubes. So inside, behind those panels, it was primarily vacuum tubes. So it was a vacuum tube-based computer. It weighed 27 tons and took up 1,800 square feet. So within a span of 50 years, we went from that to the chip that you see on the right, which is, again, smaller than a dime. Now, that was in 1995. So fast forward to today, 2021, the chip in the Apple iPhone 13, the A15 Bionic, that's the chip you see right there, that chip is at least 1.5 million times smaller because in this case, I'm looking just at the area. It's 1.5 million times smaller, but more importantly, it's 40 billion times more powerful. 40 billion. And when we think about the cost on an iPhone 13 is somewhere in the range of $700-800. Well, add 4 zeros to that because the cost of the ENIAC in today's dollars is about $7 to $8 million. Okay, so that's a pretty incredible progress, and really no other industry in history has improved that much in such a short amount of time. So that's what gets us to Moore's law, what some people have called the most important graph in human history. That's the graph you see right there on the left. So Moore's law comes from Gordon Moore, a paper he wrote in 1965. And the chart from that paper where he outlines Moore's law, that's the exact chart that you see right there. Now, there are a couple of different versions of Moore's law, actually, because Moore's law is a prediction. It's not really a law, it's a prediction. And so Gordon Moore himself changed that prediction very slightly over the years, so it can be a little confusing. But in general, when we talk about Moore's law, the most common version is that the number of transistors, so the number of switches, we talked about those switches, on a chip doubles every 2 years. Now that sounds pretty cool, but the most important part of that is that the number of switches doubles, but it doesn't cost you any more money. So in practice, what that means is every 2 years, you get a computer that's twice as fast, but you pay the same amount of money. Or on the flip side, every 2 years, you get the same computer for half the cost. So a $1,000 computer in 2 years becomes a $500 computer, becomes a $250 computer, so on and so forth. That's an exponential growth function. That sounds like a pretty good deal, right? And it is. But again, that's another understatement, because to give you a sense for how good of a deal that is, if the airline industry obeyed Moore's law, a flight from New York to Paris that took 7 hours and cost $900 in 1978 would have taken a second and cost a penny in 2005. Okay, so 7 hours, $900 to a second and a penny. Now, unfortunately, the airline industry is not the semiconductor industry. And so I looked this up the other day, and that 7-hour, $900 flight from 1978 would today still cost you about $900 and take about 7 hours. So I think that really gives you a sense for the magnitude of Moore's law, and also a sense for just how much the semiconductor industry is in a league of its own. So how does the magic happen? How are semiconductors made? As you can imagine, it's a pretty complex process, but I like to think about it in 3 buckets, so 3 steps: design, fabrication, assembly, and test. So the first step, design. Now, semiconductors have gotten pretty complex, and so the design step of a modern semiconductor can take anywhere from 1 to 3 years. These are very, very complicated devices, so complicated that like one human being can no longer understand the entirety of a chip. You know, there's when Intel makes a chip, for example, no one at Intel understands every aspect of how that chip works. It's just too complicated. So you have to break it out into teams, and it really is a very organized process. And so it takes about 1 to 3 years. Now, once that design is made, it's sent off to fabrication. In fabrication, what happens is they take a silicon wafer. So that's what you see there. That disk is a silicon wafer. So that's the semiconductor material. And what happens is we essentially take the design and we print it again and again and again and again on that silicon wafer. So what you see on that wafer, you see that repeating pattern. Those are the repeating pattern of printed chips. So that printing process, we can think of it, I think thinking of it as a printing process is a very good analogy. That printing process takes about 3 to 5 months. Now, once that printing process is finished, those chips, those wafers, those printed wafers go on to the assembly and test step. Now, in assembly and test, they take that wafer, they slice it up very carefully into the individual chips. They call them die. And then those chips are tested, and then they're packaged. So like what we saw with the individual transistor, where that tiny little black square was put inside that larger cylinder, a more complex chip that might have billions of switches. So that was one switch that we saw. Some of these designs will have billions of switches all printed on. Those will then get packaged into, in this case, the photo you see here is a protective black resin. So then they put tiny little wires inside the resin, which connect to the chip. The chip itself is encased and protected. And then those wires are connected to bigger wires that allow you to then take that chip and plug it into a board. So if you've ever opened up your computer and looked at what an Intel chip might look at, what you're looking at is the packaging. The actual silicon die is inside of that package. So That's a fairly complex process: design, fabrication, assembly, and test, 3 basic steps. What kinds of companies are involved? As you can imagine, there's actually a lot of companies involved in these steps. Now, a quick history lesson. So at the start of the semiconductor industry, the early semiconductor companies like Texas Instruments, RCA, Motorola, all of what you see here, they did internally. So these were monolithic, highly vertically integrated companies. So in the design step, well, when you want to design a chip, you need software to design a chip. Think about wanting to type up a document on your computer, for example. Well, if there's no Microsoft Word, first you have to invent Microsoft Word, and then now you have Microsoft Word, now you can type up your document. Similarly with the design process, well, we want to design a chip. Well, first we need to make software to design a chip. We want to fabricate the chip. Well, we need equipment to fabricate the chip. These companies would have to make the equipment to fabricate the chips. Now, eventually, these steps got too hard that companies really had to specialize. And so what happened after a certain amount of time was that that highly vertically integrated model, we still have those companies, and that model has kind of evolved into what we call the IDM model, the integrated device manufacturer model. These are companies like Intel, Samsung, Texas Instruments. So they still do the design, fabrication, assembly, and test steps in-house. But for the most part, they source things like the design software from companies like Synopsys and Cadence. They'll buy the manufacturing equipment from companies like ASML and Lam Research, and so on and so forth. Now, in the 80s and 90s, that IDM model further modularized into what you see at the bottom there. So as of today, the semiconductor industry is largely composed of these equipment and software, and materials suppliers that you see kind of at the periphery. And then in the middle, there's the IDMs. Then there are fabless companies. Those are companies like NVIDIA and AMD who just do design. Then there are foundry companies. So foundries are outsourced manufacturers. Those are companies like TSMC and Global Foundries. And then OSAT companies, that's outsourced assembly and test. And these are companies that do the assembly, the packaging, and the testing. Now, that sounds like a fairly complex process and a fairly complex ecosystem, and it is. But I think what you'll see as a common trend with this semiconductor industry is it's just this insanely complex industry that no one has ever heard of, and it's really not hard to it's very hard to overstate just how hard some of this stuff is. So to give you a sense for the insane scale and complexity at which the industry operates, I want to zoom in just on one tool from one supplier in just one segment for just one of these steps. Okay, so that tool is the EUV lithography system from a company called ASML based in the Netherlands. So you can think of this tool as the semiconductor printing press. And it's a really important tool. And it's one of the most important tools in the initial stages of the manufacturing process. So a single one of these tools will set you back 150 million euros. It weighs 180 tons. And the lead times are a minimum of 12 months. So just to ship one of these tools, it takes 3 entire Boeing 747s. So at the factory, they have to disassemble this whole system, package it up very, very carefully, and then charter 3 entire Boeing 747s, fly it to the facility, the manufacturing facility, reassemble it at the other side, and then test it. The technology that goes into this, EUV lithography, extreme ultraviolet lithography, that technology, the R&D on that technology started in the 80s. It took almost 40 years of R&D before that technology was commercially viable. That's how much foresight and how much investment had to go into just one of the tools, one of the dozens of tools that are used in manufacturing modern semiconductors. Now, this is obviously one of the most advanced and leading edge tools, but still it's just one of the dozens of tools that go into just the manufacturing step of the semiconductor process. Now, the complexity of just that one tool, I think, gives you a sense for just the complexity of the entire semiconductor supply chain. The semiconductor supply chain is arguably the most complex and efficient supply chain in the world. So what you see in this photo is just an example of what the typical supply chain for a chip that might go into an iPhone would look like. You can see it spans tons of regions across the world. There's lots of crisscrossing back and forth. DARPA, when they were looking at their supply chain security, they did a study and they found that a single semiconductor component that they were using changed hands 15 times before final assembly, final installation. So in their words, it went from Mexico to Costa Rica to Singapore to Taiwan to the Philippines to Japan to Korea to Taiwan again to Israel to Europe and finally to China before it got installed into the fighter jet where it was going. All right, that was just one component, and that doesn't even consider what you see here, the design aspect or where the equipment came from or who's commercializing it. That was just in the manufacturing of that one chip. Now, you might think that sounds insane. Why have such a ludicrously complex supply chain? It seems, that seems somewhat unnecessary, maybe, but the answer is pretty simple, and that's efficiency. So the semiconductor industry is one of the few industries that has been able to maximize the efficiencies gained from globalization. It's been able to take full advantage of the benefits from globalization. Why? Because semiconductors are very high margin, very high value parts, but are very, very small. So it's pretty efficient to ship them. And it's very cost effective to ship them. If you think of a shipping container, well, that shipping container can hold a lot of tiny little chips, but it can hold a lot fewer. If we think like patio furniture, right? A shipping container patio furniture versus a shipping container of semiconductor parts, much more efficient to be shipping those semiconductor parts. BCG did a study, and this gives you a sense for how efficient the semiconductor industry is. BCG did a study, and they found that to meet the demand of semiconductors in 2019, if we deglobalized entirely, so if every region were manufacturing every step internally to meet the demand in 2019, the entire globe would have had to spend an additional $1.2 trillion in CapEx. So if you think about on the reverse, 1.2 trillion in CapEx is how much we save in investment by globalizing, by putting every step in the most efficient place for that step. In addition, in terms of operating expenses, so every year to meet the demand in 2019, the semiconductor industry would have had to spend an additional 125 billion in operating expenditures. So that means globalization, this highly complex, but as a result, super efficient supply chain, it saves us up to 125 billion a year in OpEx. So the net of it is that it lowers the average selling prices, it lowers our semiconductor prices by about 40%. Now, we can't talk about the globalized complex semiconductor supply chain in today's day and age without kind of talking about some of the geopolitical concerns. So with efficiency, obviously comes some degree of fragility. And there's always a trade-off between efficiency and fragility, right? So if you think of a bullet train, for example, very few forms of transportation are more efficient than a bullet train, but also very few forms of transportation are more inflexible. How do you beat a bullet train? Well, you just step 2 steps to the right where there's no track and it can't go there. So similar with the semiconductor supply chain, you can think of it as a bullet train, super, super efficient. But as a result, we've ended up building into it some degree of fragility. And with the current geopolitical landscape, that's really come to the fore as well. So without diving into or getting too far into that rabbit hole of geopolitics, I do want to address a few what I see as common misconceptions about what's going on in the geopolitical aspect of the semiconductor industry. So the first misconception I want to talk about is this idea that somehow China has taken over the semiconductor industry. Somehow the semiconductor industry is now a Chinese industry. China makes all of our chips. If China cuts us off, we'll be in trouble. Et cetera, et cetera. Well, so that's not really true. Now, what is true is that China dominates the assembly and test part of the semiconductor process. So if you look at this chart that I have here, you can see China is responsible for 38% of semiconductor manufacturing. is 38% of the assembly and test step. Now, why does that matter? Well, that means that China finishes all of the chips. So that means that most of our chips get sent from China. So it can look like all of our chips are being made in China, but they're actually just getting finished. They're getting packaged in China and then shipped from China. So really sometimes when you look at the statistics, it can be really helpful to try and look one step further. And one of the things you'll see, at least in this case, is that China assembles all of the chips, but they don't necessarily make all of them. Now, why does China assemble all of the chips? Well, a hint to the answer is that bottom line there, where you can look at the typical gross margins for each of these steps. So that assembly and test step, what are typically called the back-end processes, that's the lowest margin part of the semiconductor manufacturing process. And it's very labor intensive. And it requires a lot of people, a lot of human capital. And so that's where China has historically been able to have a comparative advantage. So that's why actually why China dominates the assembly aspect is really a result of the efficiency of the globalization and of the efficiency of the semiconductor supply chain. Now, on the other side, the US really dominates the design side, which is the highest margin side. That said, if you look at our manufacturing in general, semiconductor manufacturing, Asia altogether, so that's China, Taiwan, Korea, Japan, all of Asia manufactures 72% of semiconductors. So that's still quite a bit in Asia. And then 81% of the assembly and test step happens in Asia. And that is one of the bigger concerns. So you'll often hear about the manufacturing of semiconductors all being in Asia. And that is a security concern. But we have to ask why, how did we get there? And because we can't really know how to fix that until we understand what caused it. All right, so Asia does make most of our chips, 72% of the chips. But the reason for that, if you've been on any of Eventide's presentations prior to this, you'll sometimes hear us talk about this transition to the knowledge economy and this shift away from the dominance of tangible assets to intangible assets. And that's really what's happened here. So if you look at the US, with all of our technology resources, with all of our talent, the US has doubled down on where the best bang for our buck is. And that's been in the highest margin parts of the process, that's been in the design process. And as a result, the design process is a very intangible asset heavy process. It's a knowledge and skill heavy process. And so if you look at R&D spending for the entire industry, the US is responsible for 60% of the entire industry's R&D spending. That's more than double all of Asia combined. So China, Taiwan, Korea, Japan. The US spent more than twice as much as all of those countries combined. That's on the intangible asset side. But you look at CapEx, so the tangible asset side, is the exact opposite. The tangible asset investments are dominated by Asia, and the US is responsible for less than half of what Asia spent, 28% versus 63%. But I think that's important in terms of context for understanding how we got to the current geopolitical situation. And it's really a result of how interconnected the supply chain got to take advantage of a lot of the efficiency supplied by globalization. And so the semiconductor industry is not a Chinese industry or a US industry or an Asian industry or a European industry. It's really a global industry, and as a result, it's really resulted in mutual interdependence. So China, the US will be in trouble if Asia stops making chips for us, but Asia can't really make chips without the US's know-how. And so there's really this kind of tit for tat mutual interdependence that undergirds the entire industry. So that's how semiconductors are made, where they're made. Now, I want to end with talking a little bit about our theme, Beyond Moore's Law. So what is Beyond Moore's Law? We talked about Moore's Law. It was that exponential growth of transistors, that increase in transistor density that allowed you to have the same computer for half the price every 2 years. It's the same law that if the airline industry followed, would have taken your $900 7-hour flight, taken that flight, and it would have cost you a penny and taken less than a second today. So that's Moore's Law. Now, the problem is that Moore's Law has been slowing down. we're actually off by about 15x. So if you look at this chart, the blue line is what Moore's law predicts. So the blue line is what Moore's law forecasts we should have in terms of number of transistors. And the red line is what we actually have. And what you see is that at this point in time, we're off by about 15x. Now, as an investor, you might look at that and say, that's pretty discouraging. If Moore's law is dead, why should we invest in technology? Isn't innovation over? But you would be wrong, because Moore's law is not the whole story. If we zoom out and we look at computational technology over a span of something, 120 years, so we zoom out and look at the broader history to understand where we're coming from, what we'll see is that Moore's law is not the whole story. In fact, Moore's law is just one phase. It was just one way in which computational technology improved. And this is a common misconception about Moore's law. People tend to think that Moore's law is a prediction about all of technology. It's not. It's about one way in which one particular kind of technology progressed. Now, it's a very, very important way, but it's not the only way. So Moore's law, increasing the number of transistors, is not the only way computers have gotten better. And it's not the only way that they can get better from here. Why is that? At the end of the day, transistors don't really matter. The number of switches doesn't really matter. What matters is that you're getting the job done better, faster, cheaper, more efficiently. And doubling the number of transistors for a very long time doubled our computational performance, but it was the performance that mattered, not the transistors. So when we start focusing too much on the transistors, it's kind of putting the cart before the horse. And doubling the number of transistors now, the slowing down of Moore's law, it's slowed down because doubling the number of transistors doesn't get us the same performance boost as it used to. So Moore's law is running out of steam, but that doesn't mean that performance improvements are running out of steam. In fact, innovation has actually accelerated because all of a sudden, with the slowing down of Moore's law, the traditional way in which we were able to improve our technology wasn't working as well. But necessity is the mother of invention. And as a result, the entire industry has undergone this paradigm shift away from thinking just about individual transistors, how many transistors can I cram on this chip, to thinking about system performance. So Art Degias, the co-founder of Synopsys, another kind of legend in the industry, he likes to talk about this, what he calls SysMoore, so that's system Moore's law. And he really argues that, look, Moore's law is slowing down, but systemic complexity continues at the same pace, at that same exponential pace. And the way we're able to do that is by getting all hands on deck, right? So attacking this problem from every possible angle. And as investors, that's very, very exciting for us because I think it actually adds more variables to this technology, which makes this, in some sense, the industry harder to understand and a little more complex, but it also creates a lot of opportunities for real innovation. And also, as an investor willing to do the work, creates real opportunities for genuine differentiation. So I've listed here just a few of those vectors for growth. So there's things like new transistor structure, heterogeneous integration. That's you might also hear that called advanced packaging. There's advanced new materials, software, hardware co-integration, domain-specific architectures. I'll highlight just briefly domain-specific architectures because we've actually touched on this already. When we talked about Tesla making their own chip, why did Tesla make their own chip? Well, the chip that Tesla is making is the chip that's used in their full self-driving, for their full self-driving capability. Now, if you understand that advanced driver assistance system, it's very, very computationally intensive. And just buying an Intel chip off the shelf and plugging it into the car wouldn't be very efficient and wouldn't get you the performance and reliability that you need within the power envelope, your power constraints. So what did Tesla do? They said, hey, we're going to make a custom chip specifically architected for this exact application. So it's a domain-specific architecture. It's an architecture specific for advanced driver assistance. And I think that's actually a really cool example for how the industry has been able to continue to improve system performance so that that full self-driving system was able to continue to improve without necessarily a similar improvement in the number of transistors in Moore's law. So I'm just going to close. This is my last slide. And I want to talk a little bit about why beyond Moore's law is such an important theme for us. So we've talked about what semiconductors are, how they're made, where they're made, a little bit about beyond Moore's law and a little bit about Moore's law and what's beyond it. But why is beyond Moore's law an important theme at all? Well, in a way, semiconductors are stand for all of technology. At the heart of all of our technology really are semiconductors. And if you want to invest in technology, you really need to understand semiconductors. And as a result, I think Moore's law and this idea of beyond Moore's law are a great example of how we ought to be thinking about technology in general. So one of the most important jobs for us as investors is to develop mental models about the world that accurately correspond to reality. So our mental models need to be well developed and predictive. And the only way they can do that is by accurately corresponding to the truth of reality. Now, what's the appropriate mental model when it comes to technology? So when we think about technology generally follows a pretty predictable sequence. So every technology typically follows a pattern of innovation and high growth to mass adoption, to maturation, to eventual decline. When we look at the pattern of each of these individual technologies, what we find is that every individual technology follows the law of diminishing returns. That's what we saw with Moore's law. So Moore's law drove an incredible era of innovation for the semiconductor industry. For about 50 years, it drove innovation in the semiconductor industry. But we've now reached the point where Moore's law they're rapidly diminishing returns to Moore's law. But fortunately, for Moore's law and for technology, that's not the whole story. Because when we zoom out and look at the big picture, what we see is that all technology is on an accelerating return curve. What do I mean by that? Well, all technology, the returns to technology is cumulative. The returns to technology compound. So for example, the easiest way to think about this is as soon as we make a faster computer, all of a sudden we have a faster computer that we can use to make a faster computer. So the faster a computer we make, the better a tool we have to make an even faster one. And so like knowledge, that technology is cumulative and the returns to technology compound. They get bigger and bigger and bigger. I think Jim Keller, so Jim Keller is the legendary architect behind the chips at Apple, Tesla, AMD. Jim Keller puts this very well when he says, progress disappoints in the short run, but surprises in the long run. So Moore's law is on a diminishing return curve. So in the short run, we'll probably be disappointed by Moore's law. But as investors and as society, I think that we would be much better off not assuming we're going to be disappointed, but knowing that in the long run, we're likely to be surprised. And that's what beyond Moore's law as a theme really stands for us. It really stands for this optimism about the innovation, about the continued innovation. And as a result, it prepares us to be able to invest in that innovation, to really dive deep, to understand, to think about what is going to drive the next wave of innovation, what's going to drive that next wave of accelerating returns. And so ultimately, that's why we consider beyond Moore's law to be such an important theme of human flourishing. And so with that, I'll end there. I probably went a little over, I realize. So we'll see how much time we have for questions. And Sean, I think you have a couple of announcements.
Yeah, that's great. Thanks, Christian. This is very informative. I love the way that you laid this out. I understand the industry a lot better. Can you go to the next slide? I'll do some housekeeping here quickly. This is our last webinar of the year. It's our season finale, if you will. It will be the most dramatic season finale that you've ever seen. This is Discover Values-Based Investing with Eventide. It is on December 16th from 1 to 5 p.m. Eastern Time. To register for it, go.eventideinvestments.com/discover. It is a longer event. I believe we have CE credit available for that event, but it is an entire walkthrough of what values-based investing is and what we believe are three main drivers that are compelling people to implement values-based investing into their investment practices. So join us for that. Again, go.eventideinvestments.com/discover. One more slide there. If you want to reach out to us, have any questions, and you don't have anybody to contact, send an email to info@eventidefunds.com. If you have a question, you can ask it there, or if you just want somebody to reach out to you, put your information in there and we will have someone reach out to you. So with that, we'll go to Q&A. And I want to start by asking this question, Christian. So we really focused on semiconductors as one of the business segments within Beyond Moore's Law. Can you speak to another technology or just a technology in general and Beyond Moore's Law that you're excited about?
Yeah, so Actually, I think when we're looking at beyond Moore's law, I think in particular what we're talking about is that within the semiconductor industry, uh, the way forward is going to look a lot different than in the past. And uh, actually, what's really exciting about that is that it really opens the door for a whole range of new startups. So we've seen this, some people have called it a Cambrian explosion of startups in things like specialized AI chips and the like. And actually, so beyond Moore's law, some of, I think, the avenues for moving forward and some of the most exciting avenues for moving forward really are in very unique ways of rethinking how we do computation. So it changes. This is kind of like what in the vein of what Tesla did by making their own chip, but we're making the kinds of chips using new kinds of like absolutely rethinking how we if you think of a chip like a brain, basically it's like we're creating alien brains. You know, the old chips are like human brains, say, and they do computations a certain way, and we're redesigning the architecture of these chips to be radically new. And one of the things that's enabled that, so I think one of the really cool themes here is what I like to call the democratization of design. So when we talk about that modularization of the industry, we talked about the IDM model and how the IDM model has turned into a fabless, foundry, and OSAT model. And actually beyond that, there's the software, there's all of this modularization. So while semiconductors are harder than ever to make, in another sense, they're actually easier than ever to make. Because before, if you wanted to make a semiconductor, you had to build a $1 million, now $1 billion factory. A typical leading edge semiconductor factory will cost about $20 billion today. But just like what you saw today, Ford realized, hey, we're falling behind. What's the difference? It's semiconductors. Let's try to do some semiconductors ourselves. They can actually do that because of how the industry has now been structured and modularized. So I actually think that it's that kind of shift that's one of the most exciting parts of this next wave forward. And that's really when we're thinking about beyond Moore's law and how to invest into that theme. I think that's kind of the way to be thinking about it.
So I have a question. It's specific, and so feel free if you don't have a lot to speak into it, just punt, and we will go to the next question. But in your opinion, what would be the short-term consequences to the semiconductor supply chain if China invades Taiwan?
Yeah. So I think that's a pretty big rat's nest of interconnected complexity. But I will say one thing that people don't realize is, Taiwan built out its semiconductors. So Taiwan has the strategy. They call it the Silicon Shield, right? This was a very intentional strategy of Taiwan to become essential to the world in semiconductors because they saw that as the way to protect themselves. So one is this was always intentional that there was going to be this conflict and that there was going to be this fear of China invading Taiwan, but Taiwan has all these semiconductors and so needs to be protected. That was very, very intentional. Okay, that's I think the first thing. The second thing is that China can't take over Taiwan's semiconductors. If China really invaded, what we saw with and what the point I was trying to make about the global interdependence of the semiconductor industry. So the tools that Taiwan uses, the U.S. dominates actually has I think over 50% market share in the advanced manufacturing equipment, and that equipment actually has consumable parts. So that equipment, there might be a part of that equipment that wears out, and that can only be replaced by the manufacturer. So as soon as China invades, for one, Taiwan needs a continual supply of US chemicals, parts, supplies to be able to continue the factory going. So as soon as China invades, and if the US cuts off that supply, China is not taking over any of that semiconductor capacity. And second is that increasingly, the harder semiconductors get to make, the more the value comes from intangibles, like we saw with the US. The more intangibles become important. So China can certainly take over the tangible assets, but the bigger question is, can they take over the intangible assets? Can they somehow coerce all of the engineers at TSMC or the similar semiconductor companies in Taiwan? Could they somehow get every single one of those engineers to continue working and to continue innovating and to continue focusing on operating that company the same way as before? Probably I think that's a bit more of a stretch. like what we said with the design, the manufacturing process also has gotten so hard that no single person can understand the whole thing. So you can't just get one person and say, hey, give me your knowledge. It's actually the entire company structured around this process. And that's part of what creates what has made it so hard. So I think those are maybe a couple nuances to that picture that maybe might help in understanding what's going on there.
So is there a trend at all that you're seeing as far as the United States bringing manufacturing to the States?
Yeah, and that's one of the things. So it would be pretty hard to be totally self-sufficient, right? And honestly, it would be very inefficient. And that's, the 1.2 up to 1.2 trillion in extra capex, all of that opex. But what the U.S. can do is, at least in the manufacturing side, one of the biggest cost differentials, why it's more expensive as of today to build manufacturing in the US versus like Taiwan or Japan or Korea, actually, or China, the biggest factor there is actually government incentives. And that's, it's not just like grants, but it's things like tax credits on R&D or supportive infrastructure or, a great deal on office space. And actually all of those things really add up. And I think BCG did a study, and I think they found something like 30 to 40% more inefficient. So manufacturing in the US is 30 to 40% more inefficient than in some of these other countries. And that's largely due to tax incentives. So there is some that the US can do in terms of restructuring our society around the importance of innovation. I think the Cold War really lit a fire under us to invest in STEM and our technical capabilities. And I think maybe to some degree we've lost that. And so hopefully the US can see that as really an opportunity to reinvest in that. But it's really a long game because a lot of that comes from having the right talent. Do we have the right engineers coming from the right programs and that sort of thing? So it's a very much kind of a long haul type story.
Is there any concern of forced labor or human trafficking in the supply chain of semiconductors?
Yeah, that's a great question. So as many of you know, Eventide has done a lot of work on the forced labor issue in Xinjiang. And fortunately, the semiconductor, the silicon that goes into semiconductors, the purity levels are much higher. And also, so in the 90s, early 2000s, semiconductors were the primary customer for all polysilicon. Now, if you think about polysilicon and solar panels use a lot more silicon than semiconductors. And so actually, whereas 25 years ago, semiconductors were maybe 90% of the world's polysilicon demand, as of today, it's less than 10%. It's something like 6 to 8%. So one is semiconductors use a much smaller amount of the polysilicon, and because of the additional, it's quality over quantity. But with solar panels, it's really quantity that matters, and being super, super cheap. Semiconductors are, because they're very high value, a little less price sensitive, not totally price insensitive, but a little less price sensitive, and quality really matters. So actually the supply chain tends to be run slightly parallel. It's not the exact same supply chain, and about 90% of the silicon used for semiconductors actually comes from one of 5 companies, and those companies are based in Japan, Taiwan, Germany, and Korea. So not China yet, but moving forward, this is absolutely something that we're watching and something that we're trying to stay on top of to make sure that we really can have an impact there.
Christian, thanks. This is very informative. With that, we're getting close to the hour, so we'll shut it down there. Christian, thank you for your time. There will be a replay available for this. You should be getting an email about that whenever it's available. So be looking for that, and you'll have a link for the replay. Thank you for joining us. Enjoy your afternoon.
Thank you, Sean.